Okay, so who is Wigner's friend? It's this guy, box with a qubit. And in kind of the classical paradigm, what you imagine is that he's in some box, and maybe the qubits in a superposition of up and down, equally weighted, and the friend will measure into z basis and get one of these outcomes. So far, there's nothing weird, but now we're going to put Wigner over here, who's thinking to himself, what do I think about my friend who's in the box? Specifically, we're imagining that this box is completely isolating. So it's not just a cardboard box. This is some high-tech thing that's keeping every bit of information that anybody outside the box could ever want to know inside of the box, and nothing's escaping out. There's no leakage. And so Wigner's sitting here and he's wondering, should I think about my friend once he measures the qubit as being in a superposition? Because in a sense, the friend will become entangled with this qubit as soon as he measures it. The alternative explanation would be that, it's absurd to think about your friend as being in a superposition. They are a friend, right? They're another agent, they're another observer. So why would you ever think about them as being something like an atom, like a spin that can be in superposition? So is it that this friend is in some classical mixture, like they are on the top there, where they really did get an outcome, I just don't know what that outcome is yet? Or is the friend in some quantum superposition? And like Schrodinger's cat, they are both alive and dead. They both spin up and spin down, and I just don't get that outcome until I go in and I measure the friend by asking them what happened. Just to emphasize a little bit, the state assignment by this state, this is the Bell state, and exists a measurement that can achieve this state and that state. Because the friend is measuring, right? The outcome for the friend is either up or down, which is like a mixture. So these two state assignments are different. And Wigner was asking, what is the state assignment? That's okay. That's okay.
Sometimes it's hard to press okay.
Okay. So one may say that this is some kind of stuff. He doesn't really know what state to assign. Both assignments can be differentiated using some Bell type measurement. But is there really like a contradiction or a paradox? Maybe not, right? Because, for example, when the friend opens the door, like Wigner opens the door and asks the friend, what did they get? The friend and Wigner sort of always agree, right? Because when Wigner talks to the friend, Wigner is doing a z-basis measurement on the friend. And the friend will say, oh yeah, I saw up. And Wigner says, yeah, I can see you saw up because you just told me. Right? Or the friend will say, I saw down. Wigner will say, yeah, sure, I saw that you saw down. So there's no like disagreement by it. Right? These state assignments look different and they are different. But every time Wigner and the friend talk, they always agree. There's no problem. Now, why is Wigner even asking this question? Who cares? Why even ask this question? So Wigner was originally motivated to ask this question because he was interested in the mind and body question. Right? Like, so Wigner argues that we know that physiochemical conditions of a body or system can sort of predict how conscious a being is. For example, like stones are less complicated physiologically than human beings. So they sense less as compared to human beings. Now, Wigner was asking, we know that physiochemical properties affect consciousness. The question is, does consciousness affect the physiochemical properties? And he argued that yes, it does, in the sense of a quantum measurement, right? Because when an observer, conscious observer, measures, they change the state. Now, as compared to what? As compared to an atom, right? Wigner is asking, is my friend more like me, because I'm an observer, or more like an atom, but just like qubit that's inside a box with another qubit at the other time. Right? And this is sort of like the entire motivation of the Wigner's friend paradox and extended Wigner paradox is to take this measurement problem, the collapse problem that's caused by measurement, and sort of see what kind of predictions it makes. If it would make any sense. Right. And so this was in this says that it was in 1968.
So at this point in history, the thinking is that consciousness is critical to measurement.
Yeah.
Okay.
At this point,
That's sort of that was still a thing that people, the way people thought about it.
yeah,
Maybe they still think about it. Some people think about it that way today, but
depends. We'll talk about it.
okay.
So was this like or
This is in 1968. I don't know why this just says
it's just
it's like a public
you knew it, shit like that.
but this is Wigner's original words.
I don't think he was alive.
No, he was alive.
Not, it was close. He died around then.
Really?
Yes, yeah.
So, but the point is, yeah,
Question, both historically and the context of this paradox, where do continuous weak measurements fit in?
this is 1968. This is quantum mechanics. This textbook in town is maybe Xerox textbook. So, like, the theory hasn't even developed in the open system direction.
68 was probably, what's his name from France, not going to be the guy before. Anyway,
Well, I'm not sure if people
Wigner.
actually, I'm not sure if most people thought that consciousness has any sort of effect here, but you know, at the end of the day, you make a measurement and a wave function collapses, and it's people that make the measurements. So Wigner was curious, like, well, is a measurement really something that a conscious observer can do only, or is a measurement like a physical process?
Yeah.
So how to disambiguate this? So the thought experiment is about that.
Yeah, so then this is in 1968, then for a long time. Physics, so people were like, that's not. Or they were, oh, measurement happens because of this open quantum system dynamics. Don't worry about it, it's not that complicated. But then recently there was like maybe 10 years ago, people started talking about Wigner's again. This time they wanted to extend it and look at some kind of inequality or like Nobel theorem implications of this extended Wigner's span.
I have a question.
Yeah.
Why should we believe that exists?
So it's a thought experiment. You can see,
It's to this question.
yeah, so it's a thought experiment. Whether that exists or not is irrelevant.
It's just a question of like, is that something that we should assume? That it exists.
I think we're assuming that quantum theory doesn't forbid it, right? Yeah. Therefore, we might as well be able to consider it. I think that's
The important point is that this is a thought experiment. And the idea of the experiment is usually to say, okay, here's the scenario that cooked up. This is what your theory says. Now, does the conclusion make sense to you? No. So either the scenario doesn't make sense or the theory doesn't make sense.
But the conclusion comes not from only the theory, it comes from our everyday experience. So I have to ask, should I believe that such a box exists?
But if you believe that
They
the existence brain source only are some kind of match.
we're not gonna get anywhere if we have
Anyway,
this.
yeah, this is.
We're not gonna get anywhere.
Mama beat me after. Anyway, so,
so. The kind of situations we're going to be studying for the rest of this entire talk are generally called extended Wigner's friend experiments or thought experiments, and what that means is that we're going to introduce a lot more agents. We're not just going to have one friend in a box, we may have multiple. We're not going to have one Wigner, we may have multiple. And we're going to be very precise about the assumptions going into the experiment. What assumptions we're going to use to draw conclusions about different observables and measurement outcomes going on between these different agents in boxes or not in boxes. So before I tell you exactly what the setup is between these friends and Wigners, I want to tell you what the assumptions that we're going to take into this are. The first assumption, which we're going to call assumption Q, is that agents who use the Born rule to predict a measurement outcome C will they will observe that with probability 1. So that's basically just saying we can use quantum mechanics, and it's actually even a little looser than that. We're saying that if an agent uses quantum mechanics to predict that some outcome will happen with probability 1, they can be certain that that will happen. That seems pretty reasonable, right? That's our first assumption. The second, which we'll call C, is that if agent A is certain of measurement C, agent B knows that agent A is certain, then agent B must also be certain of measurement outcomes C. So what that means is that if I can deduce somehow, either by talking to Mohsin or just from some other reasoning, that Mohsin is certain of some measurement outcome, then I must also be certain of that measurement outcome, because I know that there's some other agent using quantum theory. Why should I not have to accept that as my own? It's assumption number 2. Yes.
Does this involve somehow like Mohsin proving to you that he's certain, or are we just believing that everyone tells the truth?
Yeah, we're believing everyone tells the truth. Everybody tells the truth, and assumption based on that. That's a good question. Yeah. Okay. And the final assumption is extremely reasonable. We're going to call it S. It just says if agent A is certain of some measurement outcome, then they must also be certain that any other measurement outcome has probability 0. So if I am positive I'm going to see spin up, I must also be positive that I will not see spin down. This is also, so yeah. This QCS. QCS. Q is what we're going to refer to these assumptions as. Assumption Q, assumption C, and assumption S. Yeah, they're just labels.
So they have like original names like quantum, consistency, single outcome.
Right, it's like that stands for quantum, consistency, and single outcome. Yeah.
So the important point here is that all of these assumptions are for probability 1 events. What does that mean? The first says if using Born rule that probability 1 something is going to happen, you just take it. Say I'm certain that that's happening. And if someone else concludes with probability 1 something is going to happen, using C you conclude, okay, I believe that, I think this will happen. And S is just saying if with probability 1 you will see say spin up, then you're going to see spin up and you will never see spin down. All of these assumptions are reasonable.
But one of them has to be wrong.
So straightforward establishes a no-view theorem. But we use these assumptions to derive a prediction, which implies that at least one or more of them are false.
Q or C or S is something we're gonna have to throw away. What do you guys think? Any initial thoughts before we get into it?
Yeah, I guess. So,
Oh, yeah, I mean,
2,
we're gonna give you more of an answer than you probably.
We're gonna show you the proof.
Yes, but
but they're not going to tell you which one is the right one.
yeah,
So first question, you are measurement deciding probabilities was one quantum is undecidable. But in this protocol, you fix an initial state, and then you also fix the protocol. Satisfied at the dimension. Yeah. This is still undecidable if I didn't with 5-dimensional system. I forgot the exactly, but see, there is a little bit. It's about to see the terminology. But you are saying that the answer is not the creative series. This is a very well design. It's sort of its initial state and things like that. Anyway,
the finicky thing about the second assumption is that like Alex knows. We are assuming that, let's say we are asking whether all these assumptions make sense in quantum mechanics. You need to justify how an agent can know the information for something else. Like you're basically duplicating the information in one form or the other.
if you can reason through quantum mechanics that another agent is certain about some outcome, then you must also accept that.
So you can decide and select a protocol, the two of you. And then knowing that protocol, you can use quantum theory to predict what the other agent may look at. You can always do that. It's like if it tells me the experiment, I can use quantum theory to figure out what it's going to get. C is saying, once I've figured out what Andrew is going to get, I take it for granted. I just say, okay, Andrew is going to see spin one with probability one. That's going to happen. Sure. And everything also. Now it's
So it's like number two, you're assuming you have some POVM that you can measure the other agent.
it's not even about a procedure. It's like internal reasoning based on initial states.
Yeah, I'm just saying so because I feel like if you're gonna do this scenario, you need to reword everything on this, right? That's because the statements themselves are kind of not well defined, right? So they're
Skipping the math on purpose.
okay.
You didn't want to put math in here. You will see something.
No, what we say.
Anyway, so what are the implications of this result? So we just, this paper establishes that Q, C, and S cannot be true at the same time. Now, one of them has to be false. Now, the question of which one is false depends on who you ask. So if you ask John DeRota, he will say, are you crazy that you will take other people's reasoning like for granted as is without like taking your own reasoning into account? So John will say C is just absurd. That's too strict. We shouldn't take C. Like C shouldn't be true.
I'll point out that they're alluding to cubism when you say
it's-
that.
Yeah, it's like yeah. And you know, like then collapse theory people will say, of course you can do C, right? That's how we do physics, right? Like, yeah, if you think someone's gonna measure something with probability one, that's what it is. This is how physics is done, right? It's in the agent. But what the real problem is the Q quantum theory, as it's described conventionally, is not the full story. That you imagine there's some collapse that happens and there's like a theory associated with it that is not present in quantum theory as just here. And then there's like many worlds in creation. Many worlds says S is false, which is that say you see something, you cannot be certain that that's all that happened because there's a different branching of the universe, right?
See, now, when you said happen, assumed you meant happen in our universe. But not happening could include the other universe.
That's why there are question marks here. There are question marks here. How do agents communicate with different universes and
So maybe you think they should have just put 3 question marks.
I should give interpretation, invalidates C, like, if you just have somebody in the hey, what's up? That's,
I think it's because we'll say humans are classical or something like that. Right? Like, I'm not necessarily
So, like,
the thing is particle interpretation is not, it's like an umbrella term, so I'm not sure. Yeah. Yes.
What's CSM and ETH?
No, ETH is
I swear. they're not around the-
These ones are hidden variables, but I don't know.
Anyway, so depending on the group that you belong to, in terms of how you really or how you see it, you will include one of these or more. So the question is, how do we prove this?
So the rest of the talk is going to be convincing you that one of these has to be false.
Yeah.
Question for you.
Yeah.
If you go to the previous table. So there's 3 assumptions and one of them has to be false. Like there's a bunch of theories which that you predict which is false. And it's like, but none of them talk about any. It's not like the way to test which is false, because like in the end of the day, you're talking about numbers in previous slide.
I would say none. I think there are people within these camps that think there might be some way you could test some of these things, but I mean, I think depending on your opinion. Yeah, I would say a fair amount.
There were some experiments
testing Wigner friend scenarios, but then you have to accept that a photon is
Is a friend, exactly.
or a friend,
Yeah.
which is absurd.
Yeah, yeah, and it kind of defeats the point. of Wigner friend, in my opinion.
Just one. Here, I was talking to Sean Kettle, said, hey, how are you gonna start experiments to tell implications on fire? He said, we haven't worked on implications enough to conclude that there exists no experiment. So just. So how do you show this?
Yeah. Okay, so here is the basic setup for the kind of extended Wigner spread experiment we're gonna do. We have 4 agents, 2 Wigners, W and W bar, then 2 friends bar. And they live in L and L bar labs respectively. And all agents begin this experiment by agreeing on a protocol. We're not assuming they can lie, you know, we believe that everybody's going to follow the protocol. What friends in the box can do is measure their respective qubits, and we'll also give them the ability to pass qubit, at least in this direction between them. But then all they can do is measure it and reason about other agents. The Wigners similarly can make measurements on their friends and the labs and everything in front of them, but besides that, all they can do is shout and reason about other agents.
You said the box was an impenetrable thing where information does not flow out.
Yeah, so in this case, we're assuming that there is some small flow, and all it is that these 2 agents share an entangled qubit, but then none of that information gets out to the Wigners. Right. Well, you can put a little tunnel here.
Will that entangle all the boxes? Like,
It might, yeah. Certainly, if you're a Wigner, you would say that it was entangling boxes, but we'll get to that. Yeah. And a little bit of notation and explanation before we jump into it of the kind of measurements you're going to see. So you probably already caught on to this, but everything up here in the top has bars on it. So if you hear me say bar, or any of us, we're referring to the agents up here, and all the not bars are down here. And the friend here can flip a coin and prepare a qubit, and like I said, they can pass it down here. And then the 2 Wigners can measure their respective boxes. We're going to have Wigner bar here measure in the, he has the ability to measure the coin in the plus or minus superposition basis. And this Wigner down here, W, can measure the entire lap, the tensor product of the spin that he will be given and the frame in this positive negative superposition basis. It looks like a Bell state measurement, right? So these are the measurements and the notation that we're going to use in this experiment. Okay, so what is the actual protocol that they're all agreeing to? Here's the protocol. It's going to seem really complicated, but we're going to try to just work through this. So this first friend up here, F bar, is going to flip a biased coin. There's a 1/3 chance that she will get heads, and a 2/3 chance she will get tails. If it is heads, they prepare spin down, and if it's tails, they prepare this positive superposition. That's step 1. Then the bar sends the qubit down to F, who will measure the spin in the Z basis and get either up or down. Step 3 is that W bar will measure the coin in this basis. And we're going to refer to the positive superposition as fail. Hopefully it'll become clear kind of why we're calling it that a little later. And the negative superposition as okay. These are just what we're calling the measurement outcomes. And finally, step 4, W is going to do a similar measurement, measuring the positive or negative superposition basis. And we're calling positive superposition fail and negative okay. Okay, that's any questions?
with W bar, what did he do?
He measures the coin.
So you just like, but it's a coin, so you just like, it also has.
It's a coin. You can think of it as a spin.
He'll measure the coin in the.
It's crazy.
Oh, yes.
Yeah. The point is that that coin is in this enclosed box, and it makes it into a closed system, right? So it kind of has to be treated as one.
But I guess where I got confused is what in step 1, what is being done? Is the coin being flipped?
Sure.
and the coin is being flipped, and it then lands in either heads or tails.
That's right.
But after the fact, the Wigner bar does this measurement.
Yeah.
After it
It's
lands in
kind of-
either heads or tails.
Yeah.
So I think the coin is in a mixed state, actually, on a basis with the right weights.
That's the paradox. Yeah, bar knows the measurement outcome, Wigner bar doesn't know the measurement.
If W bar is using quantum mechanics to reason about what's in the box, then they'll probably assign this as being a superposition of heads and tails, because no information about the state of the coin exists in anything external to W.
So the coin is correlated with the state.
That's what's important, is that it's correlated, and there's a quantum entanglement
So
between
the-
the coin and the spin.
So it's not a classical coin, it's a coin that, so you have these two possibilities of pairing these two different states, conditional on the state of the coin, and the coin and the spin are entangled.
That's
So, yeah.
Yeah.
You measured the. After you prepare the spin.
Yes.
Yes.
Well, you don't prepare the state. The state is correlated with the coin.
It's only known to have bar like the coin with
It's correlated with the coin. Would you call that a preparation? But in principle, it could just be an entangled state where you have one amplitude with H down and the other amplitude with T plus.
So you imagine that Wigner bar as a unitary, so the evolution of that frame.
That's correct. But that's not possible, right? Like you can't prepare
In state, it looks exactly, the states are not out of speed side.
you can.
Let's go iron marks.
But it's not intentional. But yeah, coin is random.
So
The
it's
coin has a fixed initial state.
but what?
The coin has a fixed initial state,
It's called the ready state.
which is basically with probability 1/3, you see down, and 2/3, you see plus. So it's a superposition with the probability.
So it's not like, it's not a mixed state, the coin is
Yeah.
initially.
It's
Calling it
Well, it could be
a.
one of the point, it's still, it's a state, you're just saying it's entangled with the state.
It depends on who you ask. If you ask a friend that's box, he will say this is not entangled, but if you ask W bar outside, he'll say, well, yeah. Clearly, the coin is in this quantum state entangled to the spin.
Why would you assign? Did it automatically assign an entangled state to it? If you're outside, like you would assign a mixed state? Like,
This is a
You know, everything that's happened.
I don't think that's actually,
for F bar. Before F bar does the measurement.
But it's the coin this.
But yes, the coin is. And then F bar does the measurement.
is this actually important for the argument? Because this is, I've heard this talk a few times before, and you've never brought up this notion of it being in a coherent state. I don't think it's actually,
It is important that from the perspective of the outside observers, that the coin is in a coherent.
It's important.
Wait, the coin and the spin are.
Yes, correct.
So the coin itself doesn't have to be.
Both are.
Both are, that's the point.
From W bar.
Together,
From
are they entangled or are they not?
That's the point.
This is.
They're entangled. This is
Well,
the
if there's entangled, how is it pure?
Because, okay,
It's a
before F
perfect
bar does the
coin
measurement.
system. Is what-
Okay, okay, let me say
The same as the original
precise.
paradox. From W bar's perspective, like getting heads or tails is like, did my friend really get this one or really get that one? Or do I think of it as a superposition? So it's the same mystery.
Understand it, where,
So before F bar does the measurement. They get the point in the state. Now F bar did a measurement. Okay, that's a different, like, this time, so that says this is times zero.
But
that's not my.
the coin, I mean, but the spin has to be correlated with these different outcomes. So the state has to go, the joint state has to go to an entangled state,
At time 0 what? Yes.
goes to the entangled
I
state,
just wanted to be sure.
Yes.
That's the question.
right?
Okay, I'm gonna say,
Sure.
the question is like how the process happens, right? If F like looks at the coin and says, oh, if is it hedge, and then like I'll prepare a spin down. Is it T, then I'll prepare a plus state.
Yeah.
Versus like F does like basically some kind of control card of gate or something to entangle them. So those are very different, not from the perspective of the people outside. They're not different.
Because F has like this stored information which plays a part in what happens afterwards, right?
Sure, I mean, in the original way the paper is written, what happens is this is a point, a biased point that flips and then prepares either down or the right superposition, and it sends it on its way. If you want, you can think about that as if you're an agent outside, then what you're doing is reasoning about a closed system, so you can describe that measurement as a unitary, but that depends on where you are in this experiment of what you assign to it. Yeah.
So, wait, so Wigner knows what's happening, right? Inside the box.
Yes.
Everybody goes like, oh, everybody
Everybody
knows. Okay, so
Not everybody knows what the measurement outcomes are. Like W bar will not be able to figure out until they measure what the point.
so and that's why someone inside the box, like it's not entangled. The W bar it's entangled because he knows that it's either way was one or the other, right?
Yeah, that's
Okay.
okay. Let's try to go to this next part of it. So what we're going to focus on in this protocol is a particular run of this protocol where particular measurement outcomes happen. You can think about this like, there's lots of point measurements happening, so there's different probabilities of different ways that this whole thing could go. We are going to study a particular one and reason about it. And what we're going to study is we're going to imagine this. We're going to imagine in step one, F bar measures and gets tails. So they prepare this positive superposition. They follow the protocol, send it down to their friend. Step two, the friend measures this in the Z basis, gets spin up. Step three, W bar comes in and says, time to measure the point, and measures, okay, the negative superposition. Finally, step four, W says, okay, my turn, measures also, okay, the negative superposition. Seems like there's something strange going on here. So why have we made such a big deal? Well, we've got our three assumptions. I told you one of them must be wrong. And the reason is that if you use these three assumptions to conclude, to reason about what the probability is that both W and W bar get okay, which is both of them measuring the negative superposition. If you use these three assumptions, you'll conclude that that probability is zero. We'll show you why in a minute. You just take a step back, like I think a lot of you have been doing with this problem, and just treat the entire thing as some quantum circuit, right? And calculate what's the joint probability that you could measure for W to get bar to get a bar. You'll find that it's 1/12, and that calculation is on the board behind you if you want to see it. So just in case you don't believe us, it's the bottom one right there. So that's just taking this quantum system, looking at the overlap, taking the norm and squaring it. You get 1/12. So there's a disagreement here. If you follow this set of reasoning, you're going to conclude that this cannot ever happen, but quantum mechanics clearly allows this to happen. So something strange is going on.
Yeah, before you go there, can you
Yeah.
go back one?
Yeah.
So you notice in the step 4 measurement that you do, it's sort of incomplete, right?
Like it's missing the lab.
It's like it's a bed state measurement, right? So you need to have 4 outcomes, but you need 2 outcome measurements.
This entire protocol is about probability one events. So if you either see pass, we don't care about that. So
If you find minus, there is a possibility that both can fail.
no, if it's minus, it's okay. Everything else is fair.
It's okay. So everything else is fair.
Yeah. Also, because the friend is going to measure in the Z basis, the only states that span the space are up, up, and down, down. So you could argue this is effectively a qubit, and those other basic states actually don't span the space. But yeah.
So we can establish this calculation is just up on the board. You can stare at it for how long you want. But the tricky part is establishing this result using QC and S. So now we will go through this particular iteration that we talked about. We'll have the Wigners and friends, and they will reason. So we have some volunteers for friends. So ID is F bar, and one is F. I'm gonna be bigger W, and it's gonna be bigger W bar. And we're gonna use this table, timestamps, at each step of the protocol to make some predictions about what may happen later. Okay.
So first things first, I flip my coin and I get tails. So I prepare a spin in the right word in the right word state, the plus position, and send it over to F, maybe quantum teleportation or what have you. But with tails as my outcome, I can reason about the outcome of W's measurements. So before Wigner performs a measurement, there are two things to consider. First, I know that that the friend F is going to make a measurement of my spin, but I can't know the outcome of this measurement. And given the protocol, neither can Wigner. So from our perspective, I should consider the state remain in the plus superposition because I don't know what outcome the friend is going to make in their measurement. Secondly, I know that Vig bar is going to make a measurement on me and my lab, but I've already sent away I've already sent away the spin, and I know that the coin is in tails. It's not like I'm going to get measured and then suddenly this tails coin is going to get a little headsy. So the spin can't be affected by any measurements that Vig bar makes on me. But since the actions of neither my friend nor W bar will affect the state, and since I know how I prepared the state, I know that when Wigner measures that same spin, Wigner's going to get the plus superposition or the fail state.
Great, thank you. So just to summarize, from Ivy's perspective, the friend is in this state once Ivy sends the spin over, because Ivy knows it knows that the friend will measure the plus minus beta, right? And therefore, Ivy can conclude with certainty that when W goes into measure, W will get this state, which is the fail state.
And this is having taken into account spin, maybe doesn't know the outcome, and that W bar measures the coin.
So the state of the friend F is like the measurement that they get? Is that the
Yes.
measuring the state?
Yes. Or in F's perspective, because only F knows the outcome.
Sure, yeah.
Yeah, that's important. Okay, so in the next step, one, the bottom box here, is just gonna measure the spin. Just good old Z-based measurement.
So I measured my spin and I got spin up plus 1/2. Because I know what we agreed on the protocol, I am certain that Ivy F bar will have observed in the past tapes. From my knowledge of this protocol and that, I know that F bar must have concluded using assumption Q that Wigner will fail with certainty. From assumption C, I conclude that Wigner will fail with certainty.
Just to emphasize this a little bit, observe what's happened and knows for sure that F bar got tails, because if they've got heads, then they would have sent down for sure because it's only down. So just by doing this measurement, it includes what F bar observed for the coin. And then because now they know F bar's outcome, they can use quantum mechanics to replicate F bar's reasoning to conclude that W will observe fail. And from C, they adapt that belief. They say, I think F bar concluded with probability 1 that W will fail. And from C, I conclude that probability of W will fail.
So what one is use quantum mechanics to figure out what Ivy saw. One knows that Ivy must be positive that W will fail. Therefore, Juan is using assumption C to take that belief as his own. Yeah, and that belief that W will also fail.
Now on step 3, W bar is the last bar. So basically measures the coins, right? And announces the outcome.
So I come in and I measure this state, and I measure its being okay, which is this negative superposition. I know from quantum mechanics assumption Q that I can only get that if the friend observes spin up. That's also on the board behind you if you want to see it. The probability of W bar observing OK bar, the probability of F observing down is 0. That cannot happen. Therefore, I can conclude that F really did see spin up. So now, as W bar, I know what Juan must have seen. And if Juan saw spin up, I know that Juan can reason using quantum mechanics that Ivy must have gotten the tails. I also believe that all of these agents are accepting previous agents' beliefs as their own. I know that because Ivy is certain W will fail, Juan must also be certain W will fail. And therefore, I must also be certain that W will fail
from C.
from C. That's my step and now.
So now I'm gonna prove W comes out and it's like, I gotta measure this. Everybody thinks I'm gonna fail.
But by the way, I shout when because I'm right next to my other Wigner, I say, I got an OK bar, you're gonna fail.
Yeah, so now because W bar announces the outcome of K bar, and because W can use the same reasoning, let's say, oh yeah, W bar saw OK bar, which means must have seen up, which means must have seen tails. So using the similar argument, W concludes, I would really just fail, right? The probability that I see K is 0. So W concludes I will never see. Now, we have just included this chain of events. Here the F bar sees tails. You will never see OK bar, OK. If you use QCS, like SW, I have just concluded that. Right? But there's a finite probability that W bar, OK bar, and OK does happen. I can also do that. You may say, wait, this is all conditioned on the tails outcome. What if heads happens, right? Because that probability is sort of not, it doesn't care about the coin per se. The thing is, if F bar sees the heads outcome, it sends spin down. When you send spin down, W bar will never see OK bar. That is also there. So in that case, OK bar just doesn't happen at all. So OK could happen. That's fine. For the event OK and OK bar, using this QCS reasoning, we have concluded that it will happen. But there's a finite probability that if you repeat this protocol several times, it will happen at some point. So there's a contradiction. So what do you think? So the contradiction must be in that one of these assumptions or more are false. Questions, concerns? You should say, I don't believe you.
Why would I say I don't believe?
People have said that to me. People being one.
Yeah, so not that's right. So here you're also assuming other stuff, right? You're assuming your measurement is always perfect.
Yeah.
Why can't I say QCS is correct? What is wrong is yes, assuming I can ever have a perfect measurement.
Then you don't believe in Q.
Which is
Yeah, which is fine. You just told me that the measurement as defined, as described by projections, is not it.
So I'd like to just say it's kind of recent. To think when someone keeps hammering your head. So I would let go of assumption C, because if I know an agent, a certain someone, I also know someone that.
Sounds very easy. That's fine.
If you give a victim so much power that they can apply unitary and make you believe that you saw something else, then how can you ever accept another agent?
They can also make you forget your beliefs.
But
So whenever you do measurement, you are correlating two classical ways. That's how I think of like measurements. Like you
Why
say,
is the,
No, why?
no, I'm correlating a classical barrel with a quantum barrel. I want to measure a quantum object.
you measured quantum object and you kind of in the way destroyed its quantum message, like you know what it is, like perfect. You observed it and you made a copy of it, so you correlate it to classical. That's
What are the
way.
two classical variables?
The quantum object that whose state you know, and you made a copy of it into another place. So
Systems are like closed systems.
exactly, it doesn't operate in closed systems. So you can't talk about measurements, like what does it mean to talk about measurements in closed system? Like the fact that you are doing, you're getting one hand, the non-zero measurement. You are saying, oh, agent measured something. You are assuming that they measured in correlated in a superposition way, like you're creating an entire not in that. So there's like a fundamental difference between like what measurement means in your calculation.
But
You're not,
in my calculation, it is just a projection operator.
So I think Chaitanya's point is if you go to the picture, F can never know what the state is in because the measurement is you basically do a CNOT gate between the that comes and F. So F can like cannot know what state he is in because if you do that measurement, it becomes a classical correlation.
yeah,
But that's the point of this entire paragraph. Like, you can put F in this like this superposition, right? That's you can have put F part of the appendix. Yeah, that doesn't mean that its conclusion doesn't hold it. Because it starts with assuming quantum theory is universal and it says that it can be applied to anything that we can close in a box. I disagree with that. That's fine. That's fine.
Also kind of sounds like maybe one of the doubts you might have is that get some measurement outcome, sure. And from their point of view, they're just an up state or a down state, just in classical mixture of those two. But if F believes in quantum mechanics, should they not assign an entangled state to themselves? When
No one needs to
That
assign,
doesn't make sense.
I don't think it does. That feels address.
no one needs to assign these states themselves.
Yeah,
no.
It would be like F bar, say, okay, well, I know F is measuring, therefore now I think they're entangled.
But there is one, there's one piece of this that's missing, which was the whole story of the pointer states. In some sense, they're not the pointer of the meter has not collapsed because, yeah. And what's missing, in my opinion, of this is any other degree of freedom.
Yes.
Right, so it can still be a closed, this box can be this hypothetically closed thing. But there's another degree of freedom which we don't have access to.
Yeah.
And since we don't have access to another degree of freedom, when I trace out that, so the first question, the very first thing, is this thing a superposition of a mixed state?
Isn't it like sort of Landauer's principle where one of the friends measures he has some degree of freedom to store that in his memory? So then what happens when?
So if you
I don't know.
Okay.
So that assumes that like it's like a classical, like it's like a big you store. But if you want to do big change on the friend, the friend has to be like a quantum object, cannot store information like that anymore.
Also, we don't care in this case whether, the friend could in principle make a measurement on his qubit and then completely forget it. But what's important is that that information is still contained within the friend and within all of the particles in the environment. The state of that qubit has become entangled with the state of everything else inside that box and exclusively in that box. That's what's important.
I think it's right to say that in this box, there is only 2 degrees of freedom, the particle and the friend.
then no one can do any measurement.
Yeah, I think that's.
It's a C-non.
Again, it's the same box.
So you gotta go outside of it.
Okay, it's like a different question, like if they're only, if the university takes it, like that all the degrees of freedom are finite and you have access to all of them. Does it still make sense to talk about measurements? Yeah, I've been understand measurements is because you are. So you have access to some system and you want to do a measurement, you make it in contact with the bigger environment that you don't have any access to, and bond rule somehow pops out of it. So you can still predict out like what it's gonna be, but you don't know where it started. So then it faces back the question of, okay, if I don't have those degrees of freedom, like I don't have pointers, I don't have any of those, like what does it mean to measure for someone to do a measurement?
There's no sum.
Yeah.
That's. Yeah.
Say that again.
Person, I'm saying, if you have a purchase, that's already an infinite number of degrees of freedom, basically.
So it's like a C naught. So pretend you're on a qubit.
Yeah, but is that a measurement? Like that's an entangled.
So
I would say, I saw it happen.
That-
What are you talking about?
So you're articulating.
yes,
Yeah. So just to go back and hit the point of home, emphasize how like what these assumptions are saying. When friend measures the spin, they see it as being spin out. It's a Stern Gerlach, it goes up, I saw it. So it can't assign a superposition to itself. Or it says
You're saying someone else can assess.
someone else can. That's the important thing.
But what they actually measure is the position. They don't actually measure spin. That's
Yeah.
another. So actually, that's the most important thing.
Stern
That
Gerlach measures
there's another degree of freedom that you're not.
How can you measure spin without a field or length?
Yeah.
It's good point, man.
I feel like a lot of these so-called paradoxes. You know, like the big takeaways are always like mechanics is kind of insufficient or incomplete in some way. I think all of us believe that, like already believe that quantum mechanics is theory of everything. It's not a theory of everything. It doesn't include gravity.
Hold on, Einstein.
Quantum field theory, it's not everything.
I'm with you, but let's do a survey. How many people believe that? Raise your hands. Everyone believes that.
It's not a theory of everything.
Of course, it's not a push of everything.
That's what I'm saying. If you say quantum mechanics is complete, of course it's not.
But the way, I think that's a red herring.
Yeah.
You can say, oh, look, that red herring, yeah, that's important. But gravity and the lack of quantum mechanics explaining gravity does not help us to understand this paragraph.
Exactly.
It may say that quantum mechanics is incomplete, but not in this way.
Well, sure, there's not.
So it just gets the ways quantum mechanics is incomplete, but that has nothing to do with this argument.
No, I know. I'm just saying it's already incomplete. It's not a shock.
Who cares?
I have a question for you. Do you think our understanding of measurement as given by projection postulates and POVMs is complete? No. That's where, that's where you reject Q then. Yeah. So the point is, Muhammad has rejected Q.
Reject all of them.
So you're telling me if it seems been one half, say so. It could have been that we.
Yeah, people think they saw something and then it turns out they didn't all the time. Reasonable assumptions are not that deep.
Yeah,
So you should look into these two.
yeah, let's go back, so just to emphasize, rejecting Q is what Muhammad just did, and you were like, whoa, wait. And rejecting C is saying if I conclude that N is gonna C spin up with probability 1, that doesn't mean I should just take it as fact. That's also somewhat radical like position, right? Because as physicists, I would like to think if Muhammad did something that is a good physicist, I believe it's gonna happen with probability 1.
But are you going to accept that as a metaphysical principle that applies in literally every circumstance?
Probability 1 events.
Yeah.
I mean, some people say never assign probability one day.
That's a different thing, but this is for probability 1. And also 3 is just if you see spin up, you see spin up, dot. Maybe you didn't see it. No, that's not good. So,
Maybe the other branch.
this is the assumption that I believe the most. These two, it depends.
I think where it, in my opinion, it's what it means to see. and it comes back, right? Because you're not seeing anything in any of these things. You have because no measurement has ever happened. The other degree, a third degree freedom, which is everything else, plays a role in this, in my view. So there's the thing that's being measured, say the spin, the friend's conscious state, and everything else in that's in that box. And that everything else in that box has to be included because that matters into what will happen.
That's a really important point. I do want to highlight that. It's at least assumed by this paper, and I think it's typically assumed by people in these sorts of experiments, that the subscript to refer to a friend doesn't just refer to the consciousness or to the body, it refers to everything external to the object measured. So yeah.
Ivan's point that you could measure. Yeah. There's a paper that says measurements that are not being performed have no outcomes. So there's an extension to the Wigner's franchise loss that starts from the principle that if a measurement has not happened, then there is no outcome. What are you talking about? Right? So that, if you go to the last slide, that paper says, suppose the measurements have already happened.
Very last slide.
That, yeah, the very last slide. This is a backup slide we had. It's an extension. It supposes one, in my opinion, two important things. First, it's about any probability, so not probability outcomes. That previous paper is just about probability. Secondly, it says the measurements have already happened. You have A, B, C, X, Y. These are all outcomes. This thing has already happened. It constructs belt-like inequalities. Shows that if you use these three assumptions and you can construct inequalities that are widely defined on campus. So one of these has to be false or more. And we also show that those inequalities are different from right. That's important because you could say this looks like a bell inequality kind of setup, but it's actually not. It has strictly weaker assumptions than bell inequality setups.
Yes, I mean,
So I'm gonna say a sentence, tell me if you've ever seen it. I think this is complementary to what Ivan said, which is a qubit cannot measure itself. Or a quantum system cannot measure itself, which means like that's why like the second one kind of breaks down, at least in my opinion, which is if A measures something, like he cannot measure something that can be measured by B, which is A itself.
I think it's tricky because what if you put an agent that you believe can measure into a system that you believe is quantum, and you tell them to measure? Now the system is, do you think it's measuring itself, or do you think something else is happening? That's kind of what Wigner's friend is doing. We're putting it in a box so that we can treat it as a quantum system, and we're giving it the ability to measure. We're saying, what do we think about it now? So I think you have to grapple with that exact question, whether you think that statement is true or false.
Yeah, that's a good question. So if you do this calculation, assuming coherent superposition, whenever you know the information, but in a estimated form, superposition in the measurements, you still get zero, or
What do you mean by
like
now?
go back?
You're saying like
Go back.
if we did this experiment, the way that Wigner assigns the state to the friend is as a mixed state,
Yeah.
we'll get
Yeah.
superposition.
What do you get that calculation?
Oh, it's.
I mean, I don't know. But the point is that you use quantum mechanics.
So, but yeah,
Then you go to
you get zero then.
Well, I don't know what you get, so it's
I
consistent.
mean, if it's mixed, that means it's tangled with something outside it. It says it's a closed box.
I don't think that's necessarily what we may get a mixed state.
Yeah.
I'm an agent and I have a Stern-Gerlach machine and I flip across a coin and I decide to send you either spin up or spin down. I made that decision. I don't think anything's entangled.
You achieve.
Honestly, that's kind of the paradox. This is the paradox.
To preserve the unity of the center.
It's like interesting decisions in a box. Is there one?
The whole point of this was to make everyone mad and.
Yeah,
I'm glad the discussion going on because that's what we want. Do you want to say something about?
I think it's good. I think.
The last paper is a generalization of this. You don't need to know the details. You know,
Go read it. It's great. Or come ask us about it and we'll gladly talk to it.
this paper. Yeah, we know this paper in depth too, so we can be happy to talk to it. Oh, sorry.
So, right.
Any questions? Clap, clap.
You did your job.
Yeah.
Thank you.
Everyone's pissed. No. What?
Oh, by the way.